Light, the silent messenger of the universe, is one of the most profound mysteries in all of physics. It is not composed of matter, yet it carries pure energy across the vast emptiness of space with a precision that never changes, no matter who observes it or how fast they move. Every image of a distant galaxy, every equation of relativity, and every glimpse into the universe's first moments after the Big Bang begins with light. Through light, we learn how the universe behaves, how time flows, and how energy connects every corner of existence. It is both our cosmic measure and our celestial messenger. Light exists as both a wave and a particle, behaving in ways that challenge our most basic intuitions about nature. In some experiments, it acts as a wave, spreading out and overlapping to create interference patterns, while in others, it behaves as discrete packets of energy known as photons. This dual identity, wave and particle at once, depends on how it is observed. When traveling freely, light behaves like a wave, carrying energy smoothly across space. But when interacting with matter, it arrives in distinct quanta, each photon representing a tiny burst of energy. This strange duality is not unique to light but a property of all fundamental particles, from electrons to atoms to entire molecules, showing that the quantum world obeys probabilities and observation rather than classical certainty. Every color we perceive is a different vibration of the same underlying phenomenon. The red of a sunset and the blue of the sky are simply light oscillating at different frequencies, red slower, violet faster. Together, these form the visible spectrum, a narrow slice of the vast electromagnetic spectrum that includes invisible forms like infrared and ultraviolet. Infrared is felt as warmth, while ultraviolet carries more energy and can even burn skin. Our eyes evolved to detect only the range most abundant in sunlight reaching Earth's surface, a narrow window that nevertheless reveals an infinite array of colors and patterns. Beyond the visible lies a continuous ocean of electromagnetic energy, radio waves, microwaves, X-rays, and gamma rays, all part of one seamless field. Sunlight, which sustains life on Earth, takes just over 8 minutes to reach us, but its story begins long before that. Deep within the sun's core, hydrogen atoms fuse to form helium, releasing enormous energy in the process. Photons born there are absorbed and re-emitted countless times as they struggle outward through dense plasma, a journey that can take hundreds of thousands of years. When they finally escape the sun's surface, they race through space at light speed, traveling the final 8-minute leg before warming your skin. That warmth you feel on your face is the end of an unimaginably ancient voyage, a photon's final act after a lifetime in a star. When we gaze up at the stars, we look into the past. Light takes time to travel, and even the nearest stars are trillions of miles away. The glow we see tonight may have begun its journey years, centuries, or even millennia ago. Some of the faint smudges we call galaxies are ancient light, billions of years old, showing the universe as it was long before Earth even existed. In this way, telescopes become time machines, capturing ancient messages written in starlight and revealing the birth and evolution of galaxies, stars, and cosmic structures. By studying the color and intensity of this light, astronomers can deduce the temperature, composition, and motion of celestial bodies. Thus, the night sky is not merely a window into space, it is a portal through time itself. In the universe, nothing travels faster than light in a vacuum. This speed limit, approximately 299,792 kilometers per second, is not just a number but a fundamental boundary woven into the fabric of reality. It dictates how information, energy, and causality unfold throughout the cosmos. As objects approach this ultimate velocity, time slows down for them relative to an outside observer, and distances contract in the direction of motion, a phenomenon predicted and confirmed by Einstein's theory of relativity. To actually reach or exceed light speed would require infinite energy, making it impossible for anything with mass. Light, therefore, defines the tempo of existence, setting the universal rhythm by which cause and effect proceed. It connects space and time into a single fabric, space-time, governing everything from planetary motion to the curvature of the universe. Yet even though light is the fastest traveler, it can be slowed. When passing through transparent materials such as water, glass, or air, light interacts with atoms that absorb and re-emit its photons, effectively delaying its progress. Usually, this slowdown is minor, but under special laboratory conditions, scientists have used ultra-cold clouds of atoms to reduce light's speed to that of a slow stroll, and even to stop it entirely by transferring its information into matter, storing it momentarily before releasing it unchanged. This demonstrates that light and matter are deeply intertwined, and their relationship underpins technologies like optical fibers, lasers, and quantum computers that may redefine communication and Our human vision captures only a tiny fraction of the light spectrum, yet the universe is aglow with energies we cannot see. Infrared light, though invisible, carries warmth. Ultraviolet light, though unseen, burns skin and energizes chemical reactions. Beyond these lie X-rays, gamma rays, and radio waves, forms of light invisible to our eyes but vital to science and technology. Other creatures perceive the world differently. Bees can see ultraviolet patterns on flowers guiding them toward nectar, while snakes can sense infrared radiation from warm-blooded prey, detecting life in complete darkness. Through instruments and sensors, humans have extended their sight far beyond biological limits. Infrared cameras reveal the hidden heat of living bodies. Radio telescopes detect signals from distant galaxies, and X-ray observatories uncover the violent energy of black holes and supernovae. By translating these invisible wavelengths into data and images, we expand our understanding of the cosmos, seeing the unseen and knowing the unknowable. But the oldest light of all comes from the beginning of time itself. Over 13 billion years ago, the newborn universe was a dense, hot fog of charged particles that trapped light in its glow. As the cosmos expanded and cooled, protons and electrons combined to form neutral atoms, allowing light to travel freely for the first time. That light still fills space today as the cosmic microwave background, a faint radiation detectable from every direction. It is the oldest message in existence, a direct remnant of the moment the universe became transparent. As space stretched over billions of years, this light's wavelength lengthened, cooling it from blinding brightness to gentle microwaves. Yet it still carries subtle variations, tiny ripples that reveal where matter gathered to form galaxies and stars. By studying these patterns, scientists have learned the universe's age, shape, and composition, using this ancient glow as a map of creation itself. Every sunset, every rainbow, every beam of sunlight streaming through a window is a manifestation of light's journey across time and space. The redness of a sunset, for example, arises because blue light scatters more easily in Earth's atmosphere, leaving longer red wavelengths to paint the sky as the sun sinks below the horizon. That soft crimson hue is light stretched thin by distance, a cosmic whisper from the day's last photons. Whether illuminating galaxies or glimmering off a raindrop, light is both a phenomenon and a language, the universe's way of speaking to itself. It reveals the invisible, measures the immeasurable, and connects every atom to every star. Light is the rhythm of existence, the heartbeat of spacetime, the silent guide that lets us see, know, and dream. From the heart of the sun to the edge of the universe, from the birth of the cosmos to the warmth of your own skin, it remains the same, pure energy, endlessly moving, carrying the story of everything that ever was and ever will be, forever shining across the cosmic sea. When sunlight enters Earth's atmosphere, it encounters a sea of gas molecules and tiny particles that scatter light in all directions, shaping the colors of our sky. Shorter wavelengths, such as blue and violet, scatter much more strongly than longer wavelengths like red and orange, which is why our daytime sky appears blue while the sun itself glows a warm yellow. During sunrise and sunset, sunlight must travel through a thicker layer of atmosphere before reaching our eyes. The increased distance scatters away most of the blue and violet light, leaving only the longer wavelengths of red, orange, and gold to reach us directly. Dust, pollution, and moisture can enhance or soften this effect, creating sunsets that blaze or fade depending on local conditions. Every sunset is unique, painted by the precise mix of air molecules, humidity, and angle of the setting sun. What changes is not the sun's color but the atmospheric filter that shapes what we see, a collaboration between light and air that turns ordinary physics into breathtaking beauty. While scattered light colors our skies, another form of light, lightning, splits that sky with fierce brilliance. During a thunderstorm, electrical energy builds up between clouds and the ground, charging the air until the tension becomes too great. In a blinding instant, that charge releases as lightning, heating the surrounding air to temperatures hotter than the surface of the sun. At tens of thousands of degrees, atoms lose their electrons and transform into plasma, the fourth state of matter, glowing intensely as they discharge their energy. The light from a bolt of lightning spans nearly the entire visible spectrum, appearing white because every color blends together. The heat expands the air explosively, producing the shockwave we hear as thunder. Each bolt of lightning, though lasting only milliseconds, releases enormous energy and initiates chemical reactions that bind nitrogen from the air into compounds essential for life, molecules that later fall to Earth with rain. Thus, lightning is both a force of destruction and a creator of fertility, connecting the sky's electric fury to the nourishment of the soil. Light's power extends beyond what human eyes can see. Many animals perceive wavelengths invisible to us, unlocking worlds that shimmer beyond our comprehension. Bees, butterflies, and birds, for instance, can detect ultraviolet light, wavelengths shorter than violet, filtered out by our eyes for protection. To them, flowers reveal elaborate ultraviolet patterns invisible to humans. What appears to us as a simple yellow petal may to a bee look like a landing strip lined with dark ultraviolet markings guiding it straight to nectar and pollen. These hidden patterns, called nectar guides, are part of a coevolutionary language between plants and pollinators. Flowers advertise their resources using ultraviolet signals, while insects equipped with ultraviolet-sensitive vision respond instinctively, ensuring pollination continues across generations. Beyond flowers, ultraviolet light influences animal behavior in countless ways. Bird feathers may carry ultraviolet highlights that signal health or fertility to potential mates. Fruits might reflect ultraviolet hues indicating ripeness, and even rodent urine glows under ultraviolet, creating scent trails visible to predators and prey alike. Humans, protected by the filtering properties of our corneas and lenses, experience a narrower, safer slice of the electromagnetic world, but with technology, ultraviolet cameras and special sensors, we can now see the unseen. Through these tools, scientists uncover ultraviolet patterns on petals, glowing plumage on birds, and invisible contrasts in everyday materials. These discoveries remind us that human vision is just one perspective in a far broader, radiant spectrum of reality. As light journeys through different substances, it bends, slows, and sometimes splits apart in mesmerizing ways. When light passes from air into water, for instance, its speed changes, and it bends, a process called refraction. This bending explains why a straight straw appears broken or kinked when viewed through a glass of water, and why fish beneath the surface appear closer than they truly are. Refraction underlies the operation of every lens, from the human eye to cameras, microscopes, and telescopes. It occurs because different materials delay light by varying degrees, determined by their refractive index. The angle at which light enters a surface also influences how much it bends, which is why shallow glances across a lake distort reflections more than direct downward gazes. Prisms exploit this effect to separate white light into its component colors since each wavelength bends by a slightly different amount. This same principle explains the sparkle of crystals, the shimmer of glass, and mirages dancing above hot asphalt on summer days, illusions born from the simple redirection of light's path. Among the most enchanting demonstrations of refraction is the rainbow. Though it appears as an arch across the sky, a rainbow is in fact a complete circle, visible in full only from above, such as from an airplane or mountain peak. Each raindrop acts as a tiny prism. Sunlight enters the droplet, slows, bends, reflects off the back, and bends again as it exits. In doing so, it separates into colors that emerge at specific angles relative to the observer. Because of this geometry, no two people ever see the same rainbow. Each person's view is created by a unique collection of droplets aligned with their own eyes. The lower half of the circle is usually hidden by the ground, but its invisible continuation arcs below the horizon. Fog, waterfall spray, and even garden mist can produce miniature rainbows under the same laws. A rainbow's beauty arises from the cooperation of countless raindrops, each reflecting and refracting light in its own small way, together forming a grand, fleeting masterpiece. The sharpness and vibrancy of the colors depend on droplet size. Larger drops create bright, well-defined bands, while smaller ones yield softer hues. Subtle winds deform droplets, adding shimmering textures. Sometimes, a faint secondary rainbow appears outside the primary one, its colors reversed because the light has reflected twice within the drops. Every rainbow is a collaboration between geometry, optics, and perspective, a living proof that physics can paint poetry across the sky. The white light that generates rainbows is itself a symphony of all colors combined. White is not the absence of color, but the balanced mixture of every wavelength within the visible spectrum. A prism or diffraction grating reveals this truth by spreading the blend into a smooth continuum of hues from red to violet. The human eye perceives white when its three types of cone cells, sensitive to red, green, and blue, are stimulated in equal proportions, and the brain interprets that harmony as neutral light. However, not all whites are the same. Sunlight provides a nearly even balance of all wavelengths, producing what we call natural white. Artificial sources, like lamps or LEDs, often favor particular regions of the spectrum, yielding warmer, reddish, or cooler, bluish tones. Photographers, filmmakers, and designers carefully adjust for these differences, known as color temperature, to maintain realistic hues under varied lighting. Astronomers, too, analyze starlight that appears white to the eye but contains subtle spectral signatures revealing a star's temperature and chemical composition. Artists exploit the emotional and aesthetic nuances of white light, using different illumination to influence the mood of a painting or room. Far from being plain, white light is a perfect equilibrium, a chord in the symphony of color. Crystals and minerals, nature's optical artisans, reveal yet another layer of light's complexity. The internal atomic arrangement of a crystal governs how light travels through it. Some crystals, like calcite, exhibit birefringence, meaning they split incoming light into two beams that take slightly different paths and speeds through the material. When you place a clear calcite crystal over printed text, you see a double image, one beam following the ordinary path and the other an extraordinary one. Rotating the crystal makes the images shift and dance as the relationship between light and structure changes. Gemstones sparkle for the same reason. Their facets are designed to refract and reflect light internally, sending brilliant flashes outward at precise angles. Diamonds, for instance, owe their famous fire to carefully calculated cuts that maximize internal reflections, dispersing white light into vivid flashes of color. Snowflakes, quartz, and salt all owe their clarity and sparkle to the way light weaves through their orderly lattices. Even in rough stones, microscopic crystalline grains scatter light to produce the gentle shimmer known as iridescence. These interactions between light and matter form the foundation of optics and aesthetics alike, proof that beauty and physics are intertwined at every scale. Light governs not just what we see but how we interpret reality. From the scattered blue of the sky to the glowing bolt of lightning, from the hidden ultraviolet markings that guide bees to the refraction that paints rainbows, light is both a physical phenomenon and a source of wonder. It bends, scatters, and splits, revealing truths about the world's structure while enchanting the senses. The same photons that warm your skin once raced through the void of space. That same invisible energy animates every reflection, every sparkle, every color your eyes can perceive. The story of light is the story of perception, connection, and life itself, an unbroken dance of energy and matter, forever shaping how we see and understand the universe. In the atmosphere, delicate ice plates and columns refract sunlight to create halos, arcs, and bright mock suns that frame the sky, showing how even invisible order can scatter beauty across the heavens. In laboratories, scientists harness the same crystalline precision, using engineered structures to filter polarizations, tune wavelengths, and steer laser beams with immaculate control. Whether in jewelry, clouds, or instruments, crystals reveal that beauty and precision emerge from atomic order repeating in space, guiding light along paths of perfect regularity. Yet the human eye perceives only a narrow band of that cosmic radiance, a tiny window stretching from deep red to violet, shaped by evolution under the spectrum of our sun and the transparency of Earth's atmosphere. Longer wavelengths spill into infrared, microwaves, and radio, shorter ones accelerate into ultraviolet, X-rays, and gamma rays. The biological window of sight, optimized for the wavelengths that reflect richly from leaves, skin, and stone, is just one small slice of the universe's luminous conversation. Technology has allowed us to see beyond this human horizon. Infrared cameras unveil heat patterns and peer through dusty clouds in deep space. Ultraviolet detectors expose hidden minerals and fluorescent life. Radio arrays map the silent hydrogen currents between stars. And high-energy telescopes capture the violence of black holes and supernovae. Each wavelength tells the same cosmic story in a different language, showing that light is not one voice but a symphony of frequencies carrying truth across the vacuum. In the abyss of the deep ocean, where sunlight never penetrates, life has evolved its own light, bioluminescence, a chemical artistry that converts stored energy into cold, glowing fire. The deep sea, seemingly dark, is alive with moving constellations. Anglerfish dangle luminous lures that bloom like living lanterns. Jellyfish pulse with soft halos to confuse predators and attract mates. Shrimp release dazzling clouds of sparks to escape attackers. And microscopic plankton shimmer when stirred by waves or passing swimmers, sketching bright threads in the water's motion. Most of these lights are blue or green, the colors that travel farthest through seawater. Their glow, produced with astonishing efficiency, converts chemical energy into visible light with almost no heat, a natural mastery that humans have imitated in medicine and genetics, where glowing proteins trace the hidden workings of cells. In that silent underwater night, light is not luxury but language, used to communicate, camouflage, hunt, and survive. On land, another ancient artist of light flickers in the evening air, the firefly. Within its lantern cells, oxygen reacts with luciferin under an enzyme's command, creating brief, bright flashes of perfect efficiency. Each species signals in distinct rhythms, turning summer fields into orchestrated constellations of coded pulses. These living lights not only inspire awe but innovation. Scientists have borrowed their chemistry to design biological sensors and to improve LED surfaces that capture and emit light more effectively. Fireflies also serve as barometers of ecosystem health, their delicate life cycles dependent on clean water and stable wetlands. Thus, a tiny insect's flicker binds together ecology, physics, and technology in one radiant thread. The ocean, too, sometimes becomes a vast, glowing canvas. When conditions align, warm surface waters rich in nutrients, billions of plankton ignite in bursts of bioluminescence, transforming waves, wakes, and ripples into blue-green ribbons of fire. Each splash, each stroke of a swimmer's hand, becomes a brushstroke of living light. To the camera's long exposure, the sea appears to write calligraphy with its glow, each letter drawn by the reaction of a living cell meeting motion. This phenomenon, though ethereal, is pure physiology meeting physics, a response to touch that doubles as defense and spectacle, a reminder that even in darkness, nature writes poetry in light. Far above, the heavens echo that same electric artistry in grander scale. Auroras paint polar skies when the solar wind, a stream of charged particles from the sun, collides with Earth's magnetic field, funneling energy toward the poles where it meets atmospheric atoms. Oxygen releases green and red glows, nitrogen adds purples and blues, and the sky becomes a moving curtain of cosmic energy. Though the sight seems tranquil from the ground, it is powered by storms of unimaginable scale on the sun. The aurora dances, folds, and ripples as the magnetosphere flexes under solar gusts, revealing the constant electromagnetic dialogue between Earth and its star. Scientists monitor these luminous messages, for the same particles that color the sky can also disrupt satellites and power grids. The aurora, then, is both beauty and warning, a visible signature of space weather written in light. But light itself holds deeper mysteries than color and brightness. It can twist like a tornado as it travels, carrying a property known as orbital angular momentum, its wavefront spiraling in corkscrew fashion around its path. With special optical tools, physicists can imprint and manipulate this twist, creating beams that can trap and rotate microscopic particles like invisible wrenches, or encode information by varying the amount of spin. These twisted beams reveal that light is not just illumination but geometry in motion, capable of carrying structure, torque, and data. Even atmospheric turbulence can mimic these effects, shaping beams in ways that astronomers study to sharpen views through air's distortion. The revelation that light can twist reminds us how much complexity hides in apparent simplicity, each photon a tiny messenger bearing not only energy but form. Light's interaction with matter paints our world in endless variety. The ocean's color, for instance, is not its depth's reflection but a story of scattering and absorption. Water greedily drinks in red and yellow wavelengths, allowing blue to remain dominant after short journeys through the waves. Thus, the open sea appears deep blue, while coastal waters, thick with plankton, sand, or silt, turn green, gold, or brown. The sea's palette shifts constantly with wind, clouds, and surface texture, as reflections from sandy bottoms lend turquoise hues and dark rocks give indigo shades. Satellites read these tones from orbit, translating them into maps of chlorophyll and ocean health. In this way, the color of the sea becomes a living signal, not of depth but of life, changing with season and storm. The sky, too, owes its color to scattering, not pigment. Molecules of air are much smaller than visible wavelengths, and when sunlight strikes them, the shorter blue wavelengths scatter most effectively, spreading across the firmament. Our eyes, more sensitive to blue than violet, perceive the result as the dome of azure that crowns the day. Near the horizon, the path of light grows longer and the scattered blue weakens into pale tones. At sunrise and sunset, sunlight travels through even more atmosphere, stripping away its blues and violets, and leaving the sky ablaze with reds, oranges, and pinks. Distant mountains fade into bluish haze for the same reason. Shorter wavelengths scatter repeatedly, softening edges and deepening distance. Every hue we see above us is geometry at work, the dance of light with air, distance, and perception. At night, the moon glows not by its own power but by reflection, a mirror for sunlight scattered through the same physics that paints our days. Its pale shine reminds us that illumination is relational, born from interplay rather than isolation. Whether refracted through crystals, scattered by air, absorbed by water, or generated by living creatures, light connects every layer of existence, from atomic symmetry to planetary weather, from the biochemistry of fireflies to the magnetic storms of stars. It is a bridge across scales, carrying information, warmth, and meaning through every environment it touches. We live surrounded by this constant flux of photons, yet only glimpse a fraction of their journey. The universe speaks in light, in whispers of color, in bursts of radiation, in signals that cross billions of years, and to study it is to read the oldest, most intricate language ever written. Sunlight gives life to the earth, yet the moon, our silent companion, has no glow of its own. It simply reflects the sun's light, scattering it in all directions across a dusty, cratered surface that acts as a rough celestial mirror. Only a small fraction of sunlight that strikes the moon is reflected back into space, but against the darkness of the sky, that faint reflection becomes luminous enough to shape our nights. The moon's phases are merely changing perspectives of its sunlit half as it orbits Earth, while craters and mountain ranges near the terminator line cast long shadows, giving depth and texture visible even through small telescopes. Subtle hues on its face reveal mineral differences between ancient volcanic plains and brighter highlands, each feature preserving the geological memory of impacts and eruptions. During a total lunar eclipse, Earth's atmosphere bends sunlight around the planet, bathing the lunar surface in a deep copper-red glow, a projection of all the world's sunsets onto a distant sphere. For millennia, this borrowed light has guided human navigation, inspired myths and rituals, and served as a steady reference for the rhythms of nature and time itself, transforming a silent sphere of stone into an eternal companion to human imagination. The sun, by contrast, is the great architect of life. Every living thing on Earth ultimately depends on its radiance. Through photosynthesis, plants and microscopic algae capture photons of sunlight and transform them into chemical energy, creating sugars that build tissues and sustain food chains across both land and sea. Herbivores eat the plants, predators eat the herbivores, and decomposers return nutrients to the soil, completing the cycle of life that perpetually renews itself under the sun's constant watch. This energy also powers the evaporation of water, the movement of winds, and the patterns of weather and climate. Even fossil fuels, coal, oil, and gas are ancient sunlight stored by organisms that lived millions of years ago and buried their solar inheritance in the earth. Biological rhythms, from the sleep cycles of animals to the opening of flowers, are synchronized to the daily pulse of light and darkness. The tilt-of-Earth's axis modulates these cycles seasonally, cueing migrations, breeding, and flowering across continents. From the oxygen we breathe to the grain that sustains us, sunlight threads through every breath, every meal, and every heartbeat, a single star's endless generosity sustaining an entire biosphere with its quiet, radiant energy. Light also defines the very architecture of the universe, for it moves at a constant speed that no object or signal can surpass. In the vacuum of space, this speed is the cosmic limit, a boundary that enforces causality so that cause always precedes effect. No matter how fast a source moves, or how swiftly an observer travels, light's speed remains unchanged. This strange invariance, discovered through the theory of relativity, compels space and time to flex to preserve the rule. As an object nears light speed, its time slows relative to outside observers, and its length in the direction of travel contracts. Experiments with swiftly moving particles and atomic clocks confirm these effects beyond doubt. The constancy of light ensures that the universe maintains logical order, preventing paradoxes and setting horizons beyond which no influence can reach within a given time. Light is not just illumination, it is the fundamental ruler of reality, the tempo at which the cosmos keeps time. In relativity, light and gravity weave together space and time into a single dynamic fabric, space-time. The speed of light remains fixed for all observers, so the universe must stretch or curve to honor that rule. Motion slows clocks and shortens rulers, while gravity bends both space and time, altering the rate at which moments pass depending on altitude and mass. Light's path itself curves when passing near massive bodies, its trajectory bending around stars or galaxies. Astronomers exploit these warps to weigh distant clusters and map invisible dark matter, while engineers correct for them in satellite navigation systems like GPS, ensuring that time remains accurate down to the microsecond. These warps are not mere abstractions, they are measurable, practical consequences of how light defines the stage on which every event in the universe unfolds. Light serves as both messenger and metric, revealing the structure of existence while also participating in it. At its smallest scale, light is made of photons, discrete quanta of energy with no rest mass. Each photon travels at light speed, carrying both energy and momentum despite having no weight. When photons strike matter, they can push against it, exerting radiation pressure strong enough over time to sculpt comet tails, clear dust from the orbits of stars, and even propel spacecraft equipped with reflective solar sails. Light can be polarized or twisted, carrying not just brightness and color but also structure and angular momentum. In quantum experiments, single photons can interfere with themselves, or become entangled with distant partners, showing that information can be delicately encoded in their phase and polarization. Each photon is a tiny traveler, a packet of energy crossing space that may have been born in the heart of a star or from a flickering atom in a laboratory. The universe is filled with their journeys, each ray of sunlight, each glimmer of a candle flame, a stream of messengers bridging emptiness with meaning. The human eye, remarkably, is capable of detecting even a single photon. Inside the retina, specialized rod cells contain molecules that change shape when struck by a photon, setting off a chain of biochemical reactions that amplify that minuscule signal into an electrical impulse sent to the brain. Under perfect darkness, people can detect flashes corresponding to individual quanta of light, demonstrating the extraordinary sensitivity of our vision, an adaptation honed during humanity's long history of moving and hunting in the dim light of dawn and dusk. This delicate system filters out noise, allowing true signals to rise above random fluctuations, turning invisible energy into conscious perception. Each time we see light, we are witnessing energy transformed into awareness, a quantum event made personal. Other creatures push these abilities even further. Nocturnal hunters such as owls and cats enlarge their pupils and use a reflective layer behind the retina called the tapetum lucidum, which gives every photon a second chance to be absorbed. This adaptation not only enhances night vision, but also produces the familiar glowing eyes seen in the dark. Sharks and alligators share similar optical tricks, while deep-sea fish have evolved enormous eyes fine-tuned to detect the faint blue-green bioluminescence that fills the abyss. Certain snakes can sense infrared radiation, the warmth of living bodies, allowing them to hunt even in total darkness, while moths navigate by the faint polarization patterns of starlight. To these creatures, what appears as impenetrable blackness to us is a rich tapestry of motion, edges, and contrast, built from the scarce photons that reach their eyes. And when we look up into the night, the Milky Way stretches like a luminous river across the sky, a pale mist composed of billions of distant stars. Each faint spark contributes to the soft, continuous glow we perceive. The dark lanes that cut through the band are not empty but filled with interstellar dust that dims and reddens the light, tracing the spiral arms of our galactic home. Through binoculars or telescopes, the cloudy haze resolves into clusters and star fields, each a sun like our own, each with its own worlds. The light we see began its journey tens of thousands of years ago, crossing the vast void before entering our atmosphere and striking our eyes. In that moment, we connect directly to the ancient light of our galaxy, a living cross-section of a cosmic city that has shone for eons. Light, unlike sound or water waves, requires no medium to travel. Sound needs air, ripples need water, but light moves freely through the vacuum of space, sustained entirely by the self-propagating dance of electric and magnetic fields. Each oscillation of one generates the other, allowing the wave to move forward eternally, carrying energy and information without need for matter. Early scientists once imagined an invisible ether through which light must pass, but experiments disproved this idea, revealing that light needs nothing beyond the fabric of space itself. Its independence makes possible every sunrise and starlit night, as photons traverse millions of kilometers of emptiness to reach our world. Every morning, when sunlight spills across the horizon, it confirms that energy can travel across pure void. Every star that shines overhead is another proof that the universe does not need a carrier for its radiance. Light is its own traveler, its own voice, and through it, the cosmos speaks across distances too vast for anything else to bridge. From the silvery glow of the moon to the golden warmth of the sun, from the shimmer of a bioluminescent wave to the pale river of the Milky Way, all of existence is threaded by light. It feeds the forests, guides migrations, governs time, bends space, and even defines the limits of causality itself. Light is not merely something we see, it is the medium through which we understand everything else. It is energy made visible, information made real, and motion made timeless. To follow the journey of light, from the heart of a star to the surface of the moon, from a photon's birth to its arrival in a human eye, is to trace the very story of the universe, a story still being written in every sunrise and every star. Light needs no medium to travel. It moves freely through the vacuum of space, carrying with it both energy and information. Mirrors are among the simplest yet most profound tools that reveal the behavior of light. When a beam of light encounters a mirror, it follows an elegant and consistent law: the angle at which it arrives equals the angle at which it departs. This precise balance, known as the law of reflection, creates the illusion of an image existing behind the mirror's surface. Contrary to common belief, mirrors do not swap left and right. Instead, they reverse front and back. The image we see appears flipped because light reverses direction when it bounces off the reflective surface, retracing its path in the opposite direction. The quality of a mirror depends on how finely its surface is polished. Imperfections smaller than a fraction of a human hair can scatter light and distort the reflected image. A perfectly smooth surface keeps the reflected light rays organized, allowing the reproduction of fine details. This principle is at the heart of technologies that range from household mirrors to scientific instruments like telescopes and microscopes. In telescopes, massive mirrors gather faint light from distant stars, bending it into sharp focus so that astronomers can study the universe. Microscopes, on the other hand, use small precision mirrors to guide and magnify light from minuscule structures, unveiling hidden worlds in drops of water or within living cells. Every reflection, whether in a cosmic observatory or a bathroom mirror, follows the same geometry. Photons leave a source, strike a surface, and return along a predictable path determined by the mirror's shape and orientation. Yet not all mirrors behave the same way. Some reflect invisible forms of light, ultraviolet or infrared, differently than visible wavelengths. A surface that shines brilliantly under sunlight might appear dull when observed with ultraviolet-sensitive equipment, while others glow intensely in the infrared spectrum invisible to the human eye. Engineers take advantage of these selective reflections by designing multilayer coatings composed of thin films that reinforce certain wavelengths while canceling others. These coatings are the backbone of specialized instruments. Infrared mirrors help detect heat in telescopes and thermal cameras. Ultraviolet mirrors isolate energetic emissions in laboratory experiments, and laser systems rely on coatings tuned to their exact wavelength for efficiency and precision. Even window glass filters light differently across the spectrum, influencing the temperature, illumination, and comfort inside buildings. Reflection, therefore, is not a single phenomenon but a family of interactions between light and matter, shaped by wavelength, angle, and material structure. This intricate dance determines what light passes through, what bounces back, and what remains hidden from view. Another fascinating aspect of light is polarization, the orientation of its waves. Normally, light waves vibrate in all directions perpendicular to their motion. But when light reflects off surfaces like water, glass, or pavement, the waves often become aligned in one direction. This alignment produces glare, a harsh brightness that washes out colors and details. Polarizing filters counteract this effect by allowing only certain orientations of light waves to pass through, reducing reflection and restoring vivid contrast. This principle is widely used in sunglasses and photography, where it deepens blue skies, clarifies water surfaces, and reveals details otherwise hidden by glare. Many animals, including insects and birds, can detect polarization naturally, using it to find water sources, navigate by the sky's pattern of polarized light, or send subtle signals to one another that remain invisible to predators. Scientists employ polarization to study materials and internal stresses. When stressed plastics or crystals are placed between polarizing filters, the hidden forces within them appear as vibrant color patterns. Polarization adds a new dimension to our understanding of light. It is not merely about brightness or color, but about the direction of oscillation, another layer of information that light carries silently through space. Light also has the remarkable ability to interfere with itself, creating patterns of brightness and darkness. When two coherent light waves, meaning they share the same frequency and phase, overlap, their crests and troughs can either reinforce or cancel each other. Where crests meet crests, the result is bright light. Where crests meet troughs, the waves cancel out, leaving darkness. This interplay produces the iridescent rainbows seen on soap bubbles, oil slicks, and thin films, where reflections from different layers of material combine at slightly offset paths. The colors in peacock feathers, butterfly wings, and beetle shells arise from the same principle, microscopic structures that manipulate light through interference rather than pigment. In laboratories, scientists use interference as an incredibly sensitive measurement technique, capable of detecting changes smaller than the width of an atom. Interferometers, which split and recombine beams of light, can measure distances with astonishing accuracy, and even detect the faint ripples of spacetime caused by gravitational waves. Interference also reveals light's quantum nature. Even when photons are sent one at a time, their accumulated behavior forms an interference pattern, showing that each photon somehow explores multiple paths simultaneously. The universe, in this sense, is filled with invisible maps drawn by the overlapping of waves, turning geometry into visible beauty. Lasers represent one of the most extraordinary human achievements in controlling light. Ordinary light, such as sunlight or that from a bulb, consists of waves of many colors and directions, creating a chaotic mix. Laser light, by contrast, is perfectly ordered. All the waves move in the same direction, at the same frequency, and in phase with each other. Inside a laser, a special material, solid, liquid, or gas, stores energy when excited by an external source. When a single photon of the right energy passes by, it triggers nearby atoms to release identical photons, amplifying the light. Mirrors at each end of the device reflect the photons back and forth, reinforcing the process until a narrow, coherent beam escapes through one partially reflective mirror. The result is a stream of light so uniform that it can travel great distances without spreading and can be focused into an incredibly small, precise point. The term laser stands for light amplification by stimulated emission of radiation, a phrase that elegantly encapsulates how this process works. Initially inspired by microwave and radio amplification techniques, the concept was refined to operate with visible and infrared light, opening the door to countless applications. Lasers can be both delicate and powerful. In industrial settings, high-power lasers cut through steel or weld materials with astonishing precision. The energy is concentrated into a thin beam that deposits heat rapidly, melting or vaporizing a narrow groove while leaving the surrounding material untouched. In medicine, low-power lasers perform the opposite. They heal instead of destroy. Surgeons use them to reshape the cornea for vision correction, cauterize blood vessels, remove tumors, and perform intricate procedures that once required a scalpel. The key lies in tuning the beam's color, power, and duration so that only the target tissue absorbs it while nearby cells remain unharmed. The same principle that cuts metal can thus correct eyesight or seal wounds. The laser's precision, its ability to deliver energy exactly where needed, transforms light into a tool of both creation and care. The first working laser used a synthetic ruby crystal as its active medium. When a flash of intense light energized the chromium atoms within the ruby, they began releasing photons of deep red color. Each photon triggered others in a cascading effect, bouncing between mirrors until a narrow beam emerged. Though the output was modest, it proved that light could be amplified coherently, marking a turning point in science and technology. From that ruby spark, new generations of lasers emerged, using gases like helium-neon, dyes dissolved in liquids, semiconductors, and optical fibers. Each new type extended the range of available wavelengths and powers, expanding applications from barcode scanners and CD players to fiber optic communication networks and space-based instruments. Today, lasers underpin much of modern life, guiding airplanes, reading data, measuring distances to the moon, and even probing the tiniest components of atoms. Beyond their industrial and medical uses, lasers can manipulate matter at microscopic scales. A tightly focused laser beam can trap and hold tiny transparent particles, a technique known as optical tweezers. Within this focal region, the light's intensity is slightly higher in the center, creating a force that pulls small objects toward that point. Scientists use this phenomenon to hold and move individual cells, DNA strands, or microscopic beads, effectively using light as invisible fingers. These optical tweezers have revolutionized biology and physics by allowing researchers to study forces within molecules, observe molecular motors inside cells, and measure mechanical properties of microscopic materials. The fact that photons, massless particles of light, can exert measurable force demonstrates how energy and momentum intertwine in the quantum world. Light, which we often think of only as a source of vision, becomes a physical tool capable of grasping and manipulating matter. At the atomic level, light and matter engage in a constant exchange. Electrons orbiting atomic nuclei exist in discrete energy levels, and when a photon with the right energy strikes an atom, an electron can absorb it and jump to a higher level. Soon after, the electron falls back down, releasing a new photon. This process repeats millions of times per second, producing the steady glow of lamps, flames, and stars. Each element has its own unique pattern of energy transitions, which means the light it emits, or absorbs, acts as a fingerprint. Scientists analyze these patterns, known as spectra, to identify substances both in laboratories and across the cosmos. By examining starlight through a prism, astronomers can determine a star's chemical composition, temperature, and motion. For example, when sunlight is spread into a rainbow, dark lines appear at specific colors where atoms in the solar atmosphere have absorbed light. These absorption lines reveal that the sun is composed mostly of hydrogen and helium, with traces of heavier elements. Slight shifts in the positions of these lines indicate motion, showing how parts of the sun move toward or away from us. This technique, called spectroscopy, allows humanity to study celestial objects we can never touch. It bridges the gap between the laboratory and the universe, translating color into knowledge. From the reflection in a mirror to the shimmer of a soap bubble, from a surgeon's laser to the spectral fingerprint of a distant star, light reveals the hidden harmony of the universe. It travels without need of a medium, interacts with matter in ways that expose structure and order, and carries within its waves a language of geometry, energy, and information. Mirrors teach us symmetry. Polarization unveils hidden directions. Interference paints nature's colors. And lasers show how coherence can turn beauty into utility. Each beam of light, whether bouncing from glass, trapped in fiber, or racing through interstellar space, is part of a continuous story, a story of waves and particles, of order and randomness, of the eternal dance between illumination and shadow. Light serves as a universal messenger, carrying information from the smallest atom to the farthest star, revealing truths about matter, motion, and life itself through its endless variety of forms. When astronomers study the glow of distant stars, they are not merely observing brightness. They are reading a cosmic code written in the colors and patterns of light. Every beam of starlight carries within it a fingerprint, a unique arrangement of wavelengths that tells the story of the star's temperature, chemical makeup, gravity, and movement. When dispersed through a prism or spectrograph, that light splits into a rainbow streaked with bright and dark lines, each corresponding to specific atoms that have absorbed or emitted energy. These subtle marks allow scientists to determine not only what elements a star contains but also whether it is moving toward or away from us, because motion slightly shifts the wavelengths of its spectral lines. This method of spectroscopy represents one of humanity's greatest achievements in remote sensing. It allows us to study objects thousands, or even billions of light years away without ever leaving Earth. Every star, every galaxy, every glowing nebula in the night sky becomes a readable page in the vast library of the cosmos. From these spectral signatures, we have learned that stars are made mostly of hydrogen and helium, that galaxies spin and collide, and that planets orbit countless suns across the universe. Light does not merely illuminate, it communicates, bringing whispers from distant worlds through the silent vacuum of space. Sometimes, the evidence of those worlds comes not from the light they emit, but from the light they block. When a planet passes in front of its parent star, it casts a tiny shadow detectable from Earth. The star's brightness dips by a fraction of a percent, a barely perceptible flicker, but one that repeats regularly as the planet orbits. By studying the timing and depth of these dips, astronomers can deduce the planet's size, orbital distance, and even the composition of its atmosphere. If some starlight passes through that atmosphere during the transit, it acquires faint chemical fingerprints, signatures of gases like water vapor, methane, or carbon dioxide. Through this delicate measurement, scientists have identified thousands of exoplanets, ranging from massive gas giants hugging their stars to small, rocky worlds that could, under the right conditions, harbor life. Each discovery reinforces the idea that planetary systems are not rare exceptions but common structures throughout the galaxy. Light, in its gentle rhythm of dimming and brightening, points the way to entire worlds that we have yet to visit. It transforms an invisible dance between star and planet into a story of motion, chemistry, and potential habitability, reminding us that even the faintest flicker across the sky may signal the presence of another home. But light is not only the astronomer's tool, it is also the backbone of human civilization. Beneath the oceans, across mountains, and through cities, networks of glass threads thinner than a human hair carry most of the world's communication. These are fiber optic cables, and inside each one, light travels through a transparent core, bouncing internally with almost no loss of energy. Unlike electrical currents that struggle against resistance and generate heat, photons glide effortlessly at nearly the speed of light, conveying immense streams of data encoded in rapid pulses or in different colors of light. The technique known as wavelength division multiplexing allows multiple wavelengths, each acting as a separate channel, to travel simultaneously through a single strand. This means one optical fiber can carry billions of phone calls, video streams, scientific measurements, and messages at once. Along the route, optical amplifiers boost the signal without converting it back into electricity, maintaining efficiency over thousands of kilometers. Compared to traditional metal wires, fiber optics are immune to electromagnetic interference and produce almost no heat, making them the perfect medium for a global digital nervous system. Today, these silent glass veins connect continents, businesses, and families, transmitting laughter, knowledge, and emotion as organized streams of light. In this sense, humanity has turned light itself into language. Our civilization now speaks in photons. Every second, unimaginably vast torrents of luminous data traverse the planet, uniting billions of people in an invisible web of communication faster and clearer than any method before. The reason fiber optics dominate long-distance communication lies in light's unparalleled speed and purity. Electrical signals moving through copper wires face resistance and capacitance, both of which dissipate energy as heat and distort the signal over distance. Photons, by contrast, experience either effect. They encounter only the faintest scattering as they pass through glass or air. This allows optical signals to maintain their integrity over immense spans, crossing oceans and continents with minimal degradation. Satellites, too, rely on beams of light to link ground stations across the globe, while laboratories synchronize atomic clocks separated by thousands of kilometers using laser pulses traveling through optical fibers. Whether it's starlight crossing interstellar voids or laser signals carrying stock market data across the Atlantic, the principle is the same. Information encoded in photons moves faster, cleaner, and with greater reliability than electrons ever could. The modern world runs on light because nothing natural transmits information more swiftly or with greater grace. Yet light's story does not belong only to science and technology. It is also a tale of beauty. Consider the fleeting shimmer of a soap bubble drifting through sunlight. Its surface gleams with iridescent colors that seem to swirl and change every second. These colors do not come from pigments but from interference. As sunlight strikes the bubble's thin film, some light reflects off the outer surface while some penetrates, reflects from the inner surface, and exits again. The two reflections combine, sometimes amplifying a color when their waves align, sometimes canceling it when they oppose. Because the bubble's thickness changes as the liquid film drains and stretches, the colors shift continuously through greens, pinks, and purples until the film becomes so thin that it bursts, vanishing into air. Each glimmer represents a precise balance of wave paths, their differences measured in billionths of a meter. Physicists study these phenomena to understand wave interference, artists marvel at their spontaneous patterns, and mathematicians model their geometry. Within that delicate sphere of air and water, light performs its purest art, a temporary masterpiece painted by reflection, motion, and the physics of thin films. The same interplay between light and structure gives rise to the brilliant hues of butterfly wings. Unlike pigments, which absorb certain wavelengths and reflect others, structural colors arise from microscopic architectures that manipulate light through interference and diffraction. Under a microscope, a butterfly's scales reveal rows of ridges and layered nanostructures that act like tiny diffraction gratings. These structures selectively amplify certain wavelengths while canceling others, producing colors more vivid than any dye. Because the hues depend on geometry rather than chemistry, they never fade. Specimens preserved for centuries retain their luster, as if newly alive. Structural coloration also changes with angle, creating the mesmerizing iridescence that shimmers as butterflies flutter in sunlight. Scientists have drawn inspiration from these natural designs to engineer new materials for use in solar cells, anti-counterfeiting patterns, low-energy displays, and paints that never lose their brilliance. In every flicker of a butterfly's wing, nature demonstrates how geometry alone can summon color from the invisible order of light. Hummingbirds extend this principle in motion, transforming sunlight into living jewels. Their feathers appear to change color as the bird moves, emerald one instant, sapphire or ruby the next. Like butterfly wings, these feathers do not rely on pigments but on the precise arrangement of microscopic platelets made of keratin and air. These platelets act like tiny prisms, reflecting and refracting light so that its color shifts with viewing angle and intensity. As a hummingbird darts between flowers, each twist of its body reshapes the light it reflects, turning its feathers into flashes of metallic brilliance. This optical magic is the result of nature's engineering at the nanometer scale, where the spacing between structural layers determines which wavelengths interfere constructively. The same physics that allows astronomers to analyze starlight or engineers to design fiber optics also animates the shimmer of living creatures. Across scales vast and small, from cosmic to biological, light obeys the same fundamental rules, transforming structure into spectacle. Whether it is captured by mirrors, bent by lenses, or guided through glass fibers, light is the universe's most eloquent storyteller. It tells us what distant stars are made of and how planets move. It carries our voices across oceans and our images through the air. It paints the colors of wings and bubbles. It reveals both the grandest and the most delicate patterns of nature. From the cosmic to the cellular, light connects every realm of existence, weaving together physics, art, and life in one seamless spectrum. The study of light, its reflection, refraction, interference, and transmission, has shown us that the universe is not silent but constantly speaking in the language of color and wavelength. Each photon is a messenger, born in the heart of a star or within the glow of a laser diode, carrying information across space and time. And as long as there are eyes to see, instruments to measure, and minds to wonder, that light will continue to tell its stories, about stars and atoms, about beauty and knowledge, about everything that has ever shone or reflected in the vast, luminous fabric of creation. Light is one of the most extraordinary messengers in the universe, carrying information across time and space with a grace that no other medium can match. When light interacts with matter, bends through glass, reflects off crystals, or dances upon a soap bubble, it reveals not only the beauty of nature but the deep structure of the cosmos itself. Certain wavelengths interfere constructively while others cancel, and this delicate balance of interference creates colors that shift and shimmer with motion and perspective. This phenomenon, known as iridescence, gives hummingbirds their luminous glow, turning them into living jewels that change color with every flick of their wings. The iridescent feathers are not merely for beauty. They serve as tools of communication and attraction, where subtle changes in angle reveal flashes of brilliance invisible from other viewpoints. Scientists have long studied these feathers, seeking to replicate their light-manipulating structures in laboratories, and have succeeded in crafting materials that mimic the bird's shifting hues, proof that every beat of a hummingbird's wings is physics transformed into art. The morpho butterfly, too, demonstrates how light alone can create color without pigment. Its dazzling blue wings, visible from afar in rainforest canopies, owe their brilliance to microscopic layers of chitin spaced precisely to reflect blue wavelengths while canceling others. These intricate structures act like natural photonic crystals, sculpting sunlight into pure color, so powerful that a single butterfly can gleam like a piece of sky. Engineers and scientists have studied the morpho's wings to design anti-counterfeiting patterns, color-changing fabrics, and sensors that work without dyes, showing that nature's understanding of light far predates human innovation. Diamonds, in contrast, create beauty not through interference but through refraction and reflection. When light enters a diamond, it bends due to the crystal's high refractive index, slows down, and ricochets off the inner facets, splitting into the spectrum's full range of colors. The geometry of each cut determines how light escapes, whether it dazzles the eye or fades into dullness. A perfectly cut diamond channels light so efficiently that it seems to hold fire within, every glint a tiny explosion of red, blue, and green. This interplay of angle, geometry, and light is a silent dialogue between matter and physics, where brilliance is born from precision. Above us, the stars twinkle not because they themselves flicker, but because Earth's atmosphere bends their light. The air through which starlight travels is restless, filled with layers of shifting temperature and density that distort the beams. Each ripple of air bends the light in new directions, making stars appear to shimmer and change color. Planets, having broader disks, appear steadier because their light averages out these distortions. Astronomers overcome this flickering by using adaptive optics, mirrors that flex in real time to cancel atmospheric turbulence, allowing ground telescopes to regain clarity. Space telescopes, freed from the atmosphere's interference, see the universe as it truly is, sharp, steady, and pure. In orbit, they observe faint galaxies, planetary surfaces, and nebulae in wavelengths that never reach Earth's surface, like ultraviolet and infrared light. The Hubble Space Telescope, perhaps the most famous of all, has spent decades floating in silent patience, collecting light that began its journey billions of years ago. Each photon it records left its source when galaxies were still forming and stars were young. Because light travels at a finite speed, what we see through Hubble's lens is not the present universe but the ancient one. Every image is a window into cosmic history, a moment frozen billions of years in the past. Some of the faintest smudges in Hubble's deep field images represent galaxies that formed less than a billion years after the Big Bang, their light arriving now, one photon at a time, to tell the story of creation. Hubble's precise optics allow it to see details so fine they would be like spotting a pinhead from miles away. Through it, we do not merely look at the stars, we read the history of space itself. As this light travels across the expanding universe, it stretches, its waves lengthening and sliding toward the red end of the spectrum, a process known as redshift. This cosmic stretching acts like a fingerprint of expansion, letting astronomers measure how fast galaxies are receding from us. The farther the galaxy, the more its light has been redshifted, revealing both its age and its distance. This discovery proved that the universe is not static but expanding, that galaxies drift apart as space itself grows. The red glow of distant galaxies is not their true color, but the visible trace of the universe's own breath, stretching light across eons. In this way, color becomes a measure of both time and motion. Each photon arriving at our telescopes carries within it a record of cosmic history, stretched and softened by billions of years of travel. The most remarkable truth of all is that for light itself, no time passes. According to Einstein's theory of relativity, a photon traveling at the speed of light experiences no passage of time between emission and arrival. From its own perspective, the moment it leaves a distant star and the moment it reaches your eye are the same instant. For us, the journey spans billions of years. For the photon, it is timeless. This paradox, of time standing still for light, adds a profound mystery to its role in the universe. Every beam we see, every flicker from a distant galaxy, every shimmer on water or sparkle in a gem, is a timeless messenger carrying whispers from the farthest reaches of reality. From the play of color on a butterfly's wing to the faintest glimmer of an ancient star, light connects the smallest details of life with the vastest scales of the cosmos. It shapes beauty, reveals truth, and bridges the gap between the present and the beginning of time. The universe writes its autobiography in light, and we, as observers, are readers of that radiant text, decoding its language of color, reflection, and interference to glimpse the story of everything that ever was. The light striking your eyes from a distant star began its existence, and fulfilled its purpose in one continuous act, bridging the vastness of the cosmos in a single, timeless motion. Space and time are intertwined so deeply that light travels along the very edges of their union, where duration itself collapses. Every ray of sunlight, every shimmer from a distant galaxy, is both ancient and immediate. It carries no memory of its voyage, because for light, the voyage never truly happens. From the perspective of a photon, departure and arrival are the same event. The universe compresses along its line of travel, and the distance between emission and absorption shrinks to nothing. To a being made of light, time itself becomes meaningless. When a photon leaves the surface of a star and eventually touches your retina, what seems to us like a journey spanning years or centuries is, for that photon, a single continuous instant. Einstein's theory of relativity makes this paradox possible, showing that at the speed of light, both time and distance lose their ordinary meaning. This insight changes how we think about separation. The light from distant galaxies that has traveled billions of years to reach us has, from its own perspective, bridged that space in no time at all. Each beam we see is an instantaneous connection between origin and observer, joining 2 points in spacetime without delay, existing in a single eternal now. Gravity, the silent sculptor of the cosmos, bends the path of light around massive objects. Einstein predicted that gravity does not merely tug on planets and stars, it also curves the trajectories of light itself. When a beam passes near something immensely heavy, like a star or galaxy, the surrounding spacetime warps, and the light follows that curvature like a marble rolling along the bend of a stretched fabric. This effect was first confirmed during a total solar eclipse in 1919, when starlight grazing the sun appeared slightly shifted from its usual position. That small deflection became one of the most profound pieces of evidence in modern science, proving that light moves not through an invisible force field but along the curved geometry of space itself. Across the universe, this same bending can magnify and distort distant galaxies, turning them into beautiful arcs and rings of light known as Einstein rings. Massive galaxy clusters, with their immense gravitational pull, act as cosmic magnifying glasses that focus light from even farther galaxies behind them, a phenomenon known as gravitational lensing. Through these natural lenses, astronomers can observe objects that would otherwise be invisible, hidden by distance and faintness. Sometimes this cosmic magnification reveals the light of a single star across billions of light years, briefly amplified into view. Gravitational lensing also lets scientists map the invisible, dark matter, since its gravity contributes to these patterns of distortion. Thus, every bent arc of starlight becomes both a picture and a map, a living diagram of how mass shapes the universe. In this way, gravity itself becomes a tool of observation, turning space into its own telescope. Near black holes, light experiences even more extreme effects. At the edge of these cosmic abysses, gravity is so intense that photons must fight to escape, and those that do climb away lose energy, stretching their wavelengths into deep red hues. To a distant observer, this light seems to slow, fade, and freeze, suspended on the brink of nothingness. The boundary beyond which no light can return is the event horizon, the point of no return in spacetime. Just above it, however, light can still struggle outward, carrying the last whispers of matter being devoured by gravity. This phenomenon, known as gravitational redshift, is a visible manifestation of how energy and time warp together near extreme gravity. The light that escapes is stretched thin across eternity, a final message from the edge of oblivion. Even more astonishing is the photon sphere, a narrow region where light can orbit a black hole in perfect circles. Here, spacetime curves so sharply that a photon traveling tangentially can loop around the black hole endlessly. Though in reality even a tiny disturbance sends it spiraling inward or outward, this theoretical boundary is crucial to understanding black holes. The bright rings captured in images from the Event Horizon Telescope arise from photons that have circled the black hole many times before finally escaping toward Earth. These luminous halos allow astronomers to measure a black hole's size and spin, transforming light into a tool for exploring the most extreme environments known to physics. At this razor-thin boundary, gravity and geometry dance together, defining the frontier between motion and imprisonment. The bending of starlight was not merely a theoretical curiosity. It became the turning point that proved Einstein's general theory of relativity. During the 1919 solar eclipse, when daylight dimmed enough for astronomers to photograph background stars near the sun, their measured positions revealed the predicted shift exactly as Einstein had foreseen. That experiment transformed him from an obscure physicist into a global icon and reshaped humanity's understanding of the universe. It showed that even something massless, light itself, responds to the curvature created by mass. Every gravitational lens observed today, every distorted arc of a faraway galaxy, traces its intellectual ancestry to that moment when starlight bent through the sun's pull, validating one of the most revolutionary ideas ever conceived. Among the universe's brightest and most distant beacons are quasars, galactic hearts ablaze with unimaginable power. Quasars shine brighter than entire galaxies, fueled by supermassive black holes that devour surrounding matter. As gas and dust spiral inward, friction and magnetic forces heat them to millions of degrees, releasing torrents of radiation that can outshine all the stars in their host galaxy combined. Even across billions of light years, quasars appear as brilliant points of light, tiny yet impossibly luminous. Their radiance allows astronomers to probe the structure of the early universe, revealing how galaxies form and black holes grow. The light of a quasar acts as a flashlight shining through intergalactic space, illuminating the distribution of gas and elements between galaxies. Each one is a paradox of creation and destruction, where gravity's relentless pull transforms collapsing matter into radiant energy that travels across the ages. Yet even quasars are outshone, briefly, by the most powerful explosions known, gamma-ray bursts. These cataclysmic flashes unleash more energy in a few seconds than the sun will emit in its entire lifetime. They occur when massive stars collapse into black holes or when neutron stars, the dense remnants of dead suns, collide. The resulting shockwaves launch jets of high-energy photons that race across the universe, briefly becoming the brightest sources of light in the sky. Spaceborne detectors capture them as sudden blazes that fade within moments, leaving glowing afterglows across multiple wavelengths. Each gamma-ray burst offers astronomers a glimpse into the most violent processes in the cosmos, where gravity, magnetism, and nuclear forces unite in titanic events that forge the heavy elements essential to planets and life. These outbursts remind us that light is not always gentle or serene. Sometimes it arrives as a cosmic scream, a shout from creation itself, roaring through the void. Beneath all these cosmic dramas lies a fundamental truth. Every element in the universe has its own unique light signature, a cosmic barcode written in color. Each atom interacts with light in a distinct way because its electrons occupy discrete energy levels. When electrons jump between these levels, they absorb or emit photons at specific wavelengths, producing patterns that can be seen as bright or dark lines in a spectrum. Spread the light from a star or flame through a prism, and you'll see these spectral fingerprints, lines that reveal the presence of hydrogen, helium, iron, and countless other elements. With this knowledge, astronomers can determine the composition, temperature, and even the motion of celestial bodies without ever leaving Earth. Every beam of light becomes a coded message, carrying the chemical story of its source. In this way, spectroscopy transforms light into language, a means of reading the universe. From the timeless journey of photons across the void to their delicate dance around gravity's grasp, light connects everything. It ties the observer to the distant, the past to the present, and energy to the structure of spacetime itself. It reveals that distance and duration are illusions at cosmic scales, that matter and geometry weave together to shape the paths of stars and galaxies. Whether bent by gravity, stretched by expansion, or forged in stellar fury, light remains the great storyteller of the cosmos. Every flicker we see, whether from a diamond's sparkle, a quasar's flare, or the faint afterglow of the Big Bang, is a moment of pure connection, proof that the universe speaks in brightness. For all its mysteries, the message of light is simple. In its motion, the universe remembers everything, and in its presence, time stands still. Every element in the universe has its own unique light signature, a kind of cosmic fingerprint written in color and energy. This principle, known as spectroscopy, allows scientists to determine the composition of distant stars, nebulae, and galaxies without ever leaving Earth. By spreading light through a prism or diffraction grating, astronomers can read the dark or bright lines imprinted upon it, each one corresponding to specific energy transitions within atoms. Even tiny shifts in those lines reveal how fast an object is moving toward or away from us, unlocking measurements of the expansion of the universe itself. Chemists use this same idea in laboratories to identify unknown substances, decoding the subtle glow or absorption patterns of elements. In this way, spectroscopy becomes a universal language. Every atom signs its name in light, and across the cosmos, from the hearts of stars to the cold edges of galaxies, the same language is spoken. Light has also written human history in strange and sometimes tragic ways. In the early 20th century, luminous clock dials painted with radium became symbols of modern progress. Their gentle greenish glow seemed magical, numbers shining through the night without battery or flame. The secret lay in a compound of zinc sulfide mixed with radioactive radium, whose decay constantly excited the phosphor to emit light. But for the workers who painted these dials, the so-called radium girls, the glow came at a terrible price. Told the material was harmless, they shaped their paintbrushes with their lips, slowly ingesting deadly radiation. Years later, their illnesses revealed the hidden dangers of radioactivity, and their struggle transformed workplace safety and health science. Today, glow-in-the-dark materials rely on harmless phosphorescent compounds that absorb daylight and slowly release it in the dark. The soft green glow of a modern watch face is a gentle reminder of how curiosity, danger, and discovery often walk hand in hand. Fluorescent lighting, another triumph of humanity's understanding of light, begins with the invisible. Inside each glass tube, a small electric current excites atoms in a low-pressure gas, causing them to emit ultraviolet radiation. These invisible rays strike a layer of phosphor coating the tube's interior, which in turn absorbs the energy and re-emits it as visible light. This elegant conversion bridges two unseen realms, the ultraviolet and the visible, producing bright illumination without the searing heat of traditional bulbs. Engineers can tweak the composition of the phosphor to adjust the shade of white light, creating cool hues for offices, warm tones for homes, or balanced light for studios. The same principle appears in nature. Certain minerals glow under ultraviolet light, and deep-sea creatures shimmer with their own fluorescence. Each time a fluorescent lamp flickers to life, it reenacts the quiet alchemy that turns hidden energy into something the human eye can perceive. The invention of LEDs pushed this mastery even further. A light-emitting diode creates brightness through the precise motion of electrons across microscopic crystals. Inside each chip, two layers of semiconductor meet, one rich in electrons, the other deficient. As electricity flows, electrons cross the junction, releasing photons as they settle into lower energy states. The color of the light depends on the material's composition, and by adjusting it, engineers can create every hue from warm amber to cold blue. LEDs waste almost no energy as heat, shining for tens of thousands of hours with minimal loss. They power everything from tiny indicator lights to massive video walls and city street lamps, reshaping how we illuminate the world. Every LED is a miniature universe of precision, where quantum mechanics and human design cooperate to create pure, efficient light. Above all artificial sources, the greatest lamp remains our sun, a white star whose brilliance defines life itself. Though it appears yellow from Earth, that hue is an illusion born of our atmosphere. Sunlight seen from space is pure white, a balanced blend of every visible wavelength. As it filters through air, shorter blue waves scatter in all directions, giving the sky its azure tone while leaving the direct sunlight slightly golden. Astronauts beyond the atmosphere describe the sun as almost colorless, blindingly intense against the black void. The white light it sends carries the full spectrum, painting our world in endless combinations of color as surfaces absorb and reflect different portions. Plants capture its energy for photosynthesis, oceans scatter it into deep blues, and clouds turn it into soft silver. What we call sunlight is not one color but the harmony of all, and the warm tint we see from below is simply Earth's gentle touch on a star's pure radiance. In contrast to the steady sun, the flame of a candle flickers endlessly, a small and intimate theater of physics. Each flutter of its glow is caused by tiny currents of air that alter how oxygen reaches the burning wick. Within the flame, particles of soot are heated until they incandesce, creating the golden yellow core, while at the base, blue light appears where combustion is most complete. The dance of a candle is a story of balance, between combustion, convection, and chemistry. Hot air rises, drawing in fresh oxygen that feeds the fire, while every disturbance sends the flame swaying like a living creature searching for breath. Each flicker is the visible rhythm of transformation, matter becoming energy, carbon and hydrogen merging with oxygen to form invisible vapor and radiant light. It is the oldest and simplest example of humanity's relationship with fire, an energy that has always bound survival and wonder together. At night, when sunlight fades, we turn to another light, the moon. Though we imagine moonlight as pure silver, it carries subtle colors shaped by reflection and the world around it. The moon's surface reflects sunlight imperfectly, scattering it with a faint warmth that our eyes interpret as pale gray. As it travels through the atmosphere, dust and moisture tint it slightly, and when it touches snow, the ground returns a bluish sheen. Calm water mirrors it in rippling silver, while forests and deserts lend golden or greenish tones. Because our vision weakens in dim light, these hues seem almost imagined, whispers of color rather than declarations. Cameras, however, reveal their truth. Moonlight is simply sunlight translated by distance and stone, softened by night air. It reminds us that reflection can change character without changing essence, that even borrowed light has beauty of its own. Yet light is not always gentle. In moments of fury, nature wields it with terrifying splendor, as in volcanic lightning. During powerful eruptions, vast columns of ash and gas rise into the sky, where particles collide and exchange electric charges. Billions of these interactions separate positive and negative regions until the difference becomes too great, and bolts of lightning tear through the darkness. These flashes illuminate the eruption column, revealing towers of smoke and fire sculpted into glowing plasma for a heartbeat before fading. Unlike ordinary storms, these are born not of water but of rock and ash. Scientists study volcanic lightning to understand both eruption dynamics and atmospheric electricity, using the flashes as indicators that can be detected even through thick clouds. From afar, the sight is both apocalyptic and awe-inspiring, a reminder that even destruction writes itself in light. In the ocean's depths, light takes on a different role. Some jellyfish, drifting in eternal darkness, create their own glow through bioluminescence. Within special cells, a molecule called luciferin reacts with oxygen, catalyzed by the enzyme luciferase, releasing cold, blue-green light. The radiance ripples through the jellyfish's body, pulsing like a heartbeat. Some species glow constantly, while others flash in sudden bursts when threatened, creating ghostly halos in the dark water. These displays serve many purposes, attracting prey, confusing predators, or communicating across the abyss. From these simple marine lights, scientists have derived tools that illuminate biology itself, fluorescent proteins used to tag and visualize living cells under microscopes. Thus, from a drifting jellyfish came discoveries that reshape medicine and genetics. In the same way, entire coastlines sometimes shimmer with living light when microscopic organisms called dinoflagellates fill the waves. As the surf breaks or footsteps disturb the shallows, each tiny cell releases a brief electric blue glow, producing what looks like liquid fire. The light startles predators, protecting the creatures that emit it, but to humans it appears as magic, oceans sparkling under the stars as if the sky has fallen into the sea. These glowing tides remind us that light is not merely illumination but communication, transformation, and survival. Across every scale, from atomic emission lines to the shimmer of plankton, from volcanoes to the stars, light is the universe's chosen messenger. It records the past, powers the present, and hints at the infinite. Every flicker, glow, and reflection is part of one vast dialogue between matter and energy, written in the only language both understand, the language of light. These living lights appear most often in warm, nutrient-rich waters where the organisms gather in vast numbers, transforming the sea into a living mirror of the heavens. On dark, moonless nights, bays and lagoons can shimmer with every ripple and movement, turning each stroke of an oar or each passing fish into a streak of radiant blue-green flame. This ethereal glow, known as bioluminescence, is both defense and communication, a silent, chemical language spoken in photons. Within these organisms, reactions between luciferin and oxygen, aided by the enzyme luciferase, produce light so pure and efficient that it requires almost no heat, a marvel of natural engineering perfected over millions of years. Each flash of bioluminescence can serve as camouflage, distraction, or signal. Small plankton may light up to startle predators, while deep-sea creatures may use controlled glows to lure prey toward invisible jaws. The ocean's edge thus becomes a boundary between two skies, the one above filled with stars, and the one below alive with living constellations. On land, fireflies carry this same miracle into the summer night. Their warm, golden flickers are among nature's most efficient light sources. Inside tiny lanterns at the ends of their abdomens, oxygen mixes with luciferin under the influence of luciferase, releasing photons with nearly perfect efficiency, illumination without waste. While human-made bulbs waste much of their energy as heat, the firefly glows coolly, a master of sustainable light. Each species has its own flashing rhythm, an intricate code through which males and females communicate, their patterns echoing like visual songs across meadows and forests. In some places, thousands synchronize their pulses until the night seems to breathe in waves of light, a sight so astonishing that even scientists, studying it through mathematical models, find themselves in awe. The secrets of these small lights have found human use as well. Bioluminescent enzymes are now used in medical diagnostics, environmental sensors, and even art, bringing a fragment of the firefly's glow into the world of science and technology. Beyond the meadows, in the quiet eyes of night creatures, another kind of light lingers. When a flashlight or a car's beam catches the eyes of a cat, dog, or deer, the reflection that shines back is not mere coincidence but an evolved adaptation. Behind their retinas lies a reflective layer called the tapetum lucidum, a mirror that sends unabsorbed photons back through the photoreceptors, giving the animal a second chance to see. This mechanism doubles their sensitivity to light, allowing them to navigate and hunt in darkness that would leave human eyes blind. The eerie gleam we see as eye shine is actually the visible trace of this biological amplifier. Depending on species and viewing angle, it can glow green, yellow, or silver-white. To gaze into those eyes at night is to glimpse evolution's devotion to vision, its refusal to waste even a single photon. Yet light does more than guide sight, it also governs life from within. Human skin, though not a visual organ, senses light through special receptors beneath its surface. Even through closed eyelids, sunlight can reach these cells, sending signals that regulate circadian rhythms and hormone production. Morning light, rich in blue wavelengths, tells the brain that day has arrived, prompting the release of serotonin, the neurotransmitter of wakefulness and mood. This same blue light suppresses melatonin, the hormone that encourages sleep, aligning the body's chemistry with the natural rhythm of day and night. When days shorten in winter, reduced sunlight can lower serotonin levels, leading to fatigue or melancholy, a reminder of how deeply our emotions depend on light. A few minutes of morning sunshine can lift the spirit and reset the biological clock, a simple act that connects us to the ancient pulse of Earth's rotation. Even when we sleep, our bodies listen to light. Exposure to brightness through thin eyelids can shift our internal timing, awakening us earlier than expected when dawn fills a room. The skin and brain together form a network that responds to the changing tone of daylight, measuring time not with clocks but with photons. When light changes suddenly, when we step from brilliant sunshine into a dim hallway, the visual system adjusts in a matter of seconds. The pupils contract or widen, controlling the amount of light entering the eyes, while rods and cones in the retina recalibrate their chemical sensitivity. The brain then rebalances contrast, ensuring that the world remains visible and coherent. Without this adaptive process, vision would collapse into alternating blindness and glare every time light levels changed. Instead, we experience continuity, a seamless perception born of constant neural negotiation. This synchronization between body and brightness reveals the intimate partnership between life and light. Sunlight, beyond illuminating the world, shapes emotion, focus, and biological health. It triggers serotonin, lifts mood, and helps the brain align sleep and wake cycles with the turning earth. Its absence, conversely, can dull energy and invite drowsiness. Artificial light tries to fill this void but often does so imperfectly. The blue-rich glow of electronic screens, though helpful for alertness by day, confuses the body when used at night. It mimics the spectral quality of daylight, telling the brain to stay awake long after sunset. Melatonin production falters, sleep is delayed, and rest becomes shallow. Scientists now recommend warmer, amber-toned light after dark, or night mode filters that shift the spectrum to resemble firelight, the hue to which our ancestors' bodies were tuned for millennia. Healthy rest begins not only with quiet but with darkness itself, a signal as vital as any nutrient. Light affects emotion not only through brightness but through color. Warm hues, reds, ambers, and golds, evoke comfort, intimacy, and energy, while cool tones, blues and greens, suggest calm, distance, or melancholy. These responses arise partly from biology, as longer wavelengths stimulate the nervous system gently while shorter ones invoke alertness, and partly from culture, where centuries of association link blue with serenity and red with passion. Artists, architects, and filmmakers harness this psychological palette to influence feeling and perception. In hospitals, daylight balance lighting promotes healing and alertness. In homes, warmer tones encourage relaxation. The very color temperature of a bulb can alter the perceived passage of time. Cool light quickens awareness, while warm light slows it, stretching minutes into ease. Painters like Caravaggio and filmmakers like Roger Deakins use this language deliberately. Warm light to conjure safety or memory, cool light to express loneliness or fear. The difference lies not in the objects illuminated but in the emotional texture of illumination itself. Morning and evening sunlight, filtered through more of the atmosphere, naturally takes on a golden tone, while midday light, traveling a shorter path through air, appears bluer and harsher. Our eyes, tuned by evolution, read these shifts as cues for action, warm light for rest, cool light for activity. Thus, the daily rhythm of color becomes a kind of unspoken dialogue between earth and life, a conversation that regulates every heartbeat, hormone, and mood. From the shimmer of plankton in tropical seas to the quiet glow of a firefly in a field, from the gleam in an animal's eyes to the morning light through a curtain, every instance of illumination carries purpose. Light nourishes, guides, heals, and reveals. It shapes the chemistry of our brains, the behavior of our cells, and the stories of our cultures. It is both the oldest signal and the newest discovery, forever bridging matter and meaning. To follow its journey, from the depths of the ocean to the human heart, is to understand that illumination is not just a physical event but a living dialogue between energy and life. Even in darkness, light endures in memory and reflection, in the shimmer of a wave, the spark of a thought, or the warmth of a sunrise yet to come. Color temperature blends seamlessly with storytelling, showing that the perception of warmth and cold extends beyond touch, reaching into the heart of emotion and narrative. Light becomes emotion made visible, capable of turning space into mood and time into feeling, a silent language through which stories are told not in words but in glow and shadow. Yet in our quest to fill the night with light, humanity has dimmed the stars. In sprawling cities, the combined radiance of street lamps, advertisements, and glowing windows creates a dome of perpetual twilight that hides the cosmos from view. This haze, known as sky glow, reflects off dust and moisture in the atmosphere, scattering across the sky until only the brightest planets and a handful of stars remain visible. The loss is profound, not only for dreamers and stargazers but for the countless creatures whose lives are guided by the natural rhythm of light and darkness. Migratory birds lose their bearings, turtles hatch on beaches and crawl towards streetlights instead of the ocean, and nocturnal insects find themselves trapped in circles of artificial glow. To combat this, scientists and communities promote dark sky initiatives, encouraging the use of shielded lamps that direct light downward, dimmer bulbs with warmer color temperatures, and timed systems that mimic the gentle rise and fall of natural brightness. When such changes are made, the night heals. The stars return, spreading across the heavens like ancient handwriting. In remote places untouched by urban glare, the Milky Way still shines so bright that it casts shadows upon the ground, reminding us that the universe is never gone, only waiting behind our excess illumination for darkness to invite it home. For astronomers, light is not just beauty, it is information. By using filters, telescopes can isolate specific wavelengths, revealing hidden layers of the universe invisible to the naked eye. One filter may capture the red glow of hydrogen, another the soft teal of oxygen, or the golden hue of sulfur, each color tracing a different element and energy process. When combined, these filtered images expose the anatomy of nebulae, the tendrils of galactic arms, and the shockwaves of supernovae. What seems empty space in visible light often explodes with detail under infrared or ultraviolet observation. Through these techniques, scientists detect exoplanets as tiny shadows across distant stars, measure the temperatures of cosmic dust, and even map invisible magnetic fields. The lesson is clear: light is not a single truth but a layered story, a symphony of wavelengths waiting to be separated and heard in harmony. On Earth, too, life has learned to read light in subtle ways. Plants, for instance, practice a slow, patient choreography known as phototropism. When a sprout bends toward a window, it is not random but deliberate, an elegant response to unequal light exposure. The plant's cells on the darker side elongate faster than those on the bright side due to hormones called auxins that migrate away from light. This asymmetrical growth curves the stem toward the source of illumination, positioning leaves and shoots to catch the sun most efficiently. Even underground, seeds read faint cues from filtered light to decide when to awaken. Deep within the seed coat, photoreceptors detect wavelengths that distinguish between shade and sunlight. Red light signaling open ground, far red implying cover or burial. When conditions promise sustained brightness, the seed begins its quiet alchemy, breaking dormancy and sending its first green shoots upward. Farmers harness this sensitivity to control germination, while ecologists study how forest canopies sculpt light spectra to shape entire ecosystems. Thus, even before life takes form, it listens to the language of light. Once grown, the plant performs its central miracle, photosynthesis, the process by which sunlight becomes food, breath, and energy for nearly all living things. Within each chloroplast, chlorophyll molecules absorb photons and use their energy to split water, releasing oxygen and combining hydrogen with carbon dioxide to form sugars. These sugars become the foundation of every meal on Earth, from the fruit of trees to the energy that fuels human thought. The air we breathe, the warmth of our bodies, even the fossil fuels that drive our machines, all trace back to ancient sunlight captured and stored in living cells. Through this endless transformation, the sun's fire becomes life itself, a silent conversation between star and leaf that has endured for billions of years. Yet sunlight's reach extends far beyond biology. Even in the emptiness of space, it exerts force. Though photons have no mass, they carry momentum, and when they strike a surface, they impart a minute but measurable pressure. Over vast distances in time, this gentle touch moves dust, steers comets, and even propels human-made spacecraft. Engineers have harnessed this principle to design solar sails, vast, mirror-like sheets that glide through space on sunlight alone. Without engines or fuel, these vessels accelerate slowly but continuously, their motion a graceful echo of the old sailing ships that once crossed oceans on wind. Now, humanity dreams of crossing the solar system with the same elegance, trading sails of canvas for sails of light. Already, prototypes like Japan's Ikaros and the Planetary Society's Light Sail have unfurled their gleaming wings in space, proving that sunlight can indeed serve as a cosmic wind. Each reflected photon adds a whisper of momentum, and over months, these whispers become speed. It is a reminder that light not only illuminates, it moves. Its energy can guide worlds, sculpt galaxies, and carry the ambitions of an entire species toward the stars. The sheer abundance of sunlight is staggering. Every hour, the sun delivers more energy to Earth than humanity uses in an entire year. This torrent of power fuels the weather, warms the oceans, and drives every photosynthetic process. Yet we capture only a fraction of it. Solar panels, made of photovoltaic cells, turn photons into electricity by freeing electrons within their materials, and each year they grow more efficient, bringing us closer to a world powered directly by the same light that sustains our bodies. In deserts and on rooftops, fields of dark panels silently drink the sun, transforming its radiance into current. The potential is almost unimaginable, a civilization fueled not by fire or fossil, but by the ceaseless generosity of a nearby star. The sun's energy is our true inheritance, endless, clean, and free, falling equally on every ocean, desert, and leaf. Yet light, for all its gentleness, can also burn with terrible precision. When concentrated through mirrors or lenses, it becomes a weapon of heat and transformation. Ancient civilizations discovered this long ago, using polished bronze or obsidian to ignite fires and signal across distances. Today, solar furnaces gather thousands of mirrors to focus sunlight on central towers, heating fluids to drive turbines and produce power. At the heart of such a focus, temperatures soar high enough to melt metal, the once soft sunlight turned fierce and white-hot. The principle is simple: many weak rays, when aligned, become unstoppable. A slight change in angle, however, disperses them again into harmless warmth. This delicate balance between nurture and destruction embodies the dual nature of light itself. Focused, it can forge steel; unfocused, it can grow forests. Humanity has learned to wield both aspects, the creative and the destructive, with mirrors, lenses, and knowledge. Light, in its every form, remains both the gentlest caress and the most potent force in nature. Across all its roles, illuminator, messenger, power source, and sculptor, light tells a single story, the story of connection. It links stars to life, sight to emotion, growth to time. It is both the voice of the cosmos and the heartbeat of Earth. Every beam carries the memory of its source and the promise of transformation. Whether in the faint glow of a distant nebula or the warmth of sunlight on skin, light is the universe expressing itself, pure, patient, and eternal. Light has always been both a physical phenomenon and a profound symbol, a thread connecting the practical and the spiritual throughout human history. Long before modern science explained the behavior of photons, ancient civilizations discovered that crystals could concentrate sunlight. Clear quartz, obsidian, and polished bronze were shaped into curved surfaces that brought distant rays to a single burning point. In temples across the ancient world, priests used these primitive lenses to ignite sacred fires, rituals that represented divine power descending from the heavens. The act of lighting a flame with sunlight carried both spiritual and practical meaning. It symbolized the union of heaven and earth through energy itself. Cultures from Greece to Mesoamerica practiced these rituals, linking light, fire, and life in sacred continuity. Over centuries, humanity's fascination with light transformed from ritual to investigation. The same principles that once kindled ceremonial flames became the foundation for optical instruments, leading eventually to the telescope and microscope. Each glint reflected from a polished stone marked a moment when human ingenuity bridged mystery and understanding, turning sunlight into a gateway between nature and divinity. The brightness of stars became one of the earliest measures of cosmic order. Long before telescopes, astronomers classified stars by their apparent brightness, noting which burned fiercely and which barely punctured the darkness. The Greek astronomer Hipparchus devised one of the first magnitude scales, grouping stars into 6 visible categories. Modern science, though vastly refined, still uses a system derived from his observations, showing the enduring lineage between ancient eyes and modern instruments. Through this continuity, brightness evolved from an aesthetic impression into a quantitative measurement revealing distance, temperature, and power. The stars themselves have not changed, but our way of reading them has deepened immeasurably. Across ages, light has remained our most constant teacher, its language universal, from the first stargazers to the mirrored eyes of space telescopes orbiting today. Every photon carries not just energy, but also a hidden structure. Light moves forward yet also spins. Each photon contains a tiny twist of angular momentum known as spin. Though the momentum of a single photon is almost immeasurable, in vast numbers their effects become tangible. Scientists exploit this spin to manipulate microscopic particles, trap atoms, and probe quantum systems. This property, spin angular momentum, has unlocked new fields like optical tweezers and quantum communication, revealing that light possesses not just brightness and color, but orientation and structure, a secret dance woven into its waves. Every beam carries within it a spiral, a whisper of rotation, reminding us that even what seems straight and steady can conceal elegant motion within. From this understanding of photons arises another marvel: quantum entanglement. When 2 photons are born together in certain quantum processes, their properties become linked forever, regardless of distance. Measure one, and the other responds instantly, as though joined by an invisible thread across space. This strange bond, proven again and again through experiment, shows that quantum information transcends classical boundaries. It doesn't allow faster-than-light communication, but it forms the foundation for quantum encryption and teleportation, technologies that redefine what communication and connection mean. Entangled photons behave as partners in a cosmic waltz, synchronized across space by their shared birth, proving that the universe is stitched together by relationships written in light itself. Scientists have even teleported information between entangled photons. Through this process, quantum teleportation, the state of one photon is transferred to another at a distance, without any physical travel between them. What moves is not matter, but information, encoded in the quantum state itself. This delicate, precise method requires isolation from all external interference but has been achieved repeatedly, offering a glimpse into a future where light becomes the medium not just for seeing but for communicating reality itself. In these experiments, photons act as couriers of existence, carrying not just messages but the very blueprint of states across space, hinting that light is the fabric upon which the universe writes its memory. The human eye, our own most personal detector, is exquisitely tuned to this cosmic messenger. Under daylight, our vision peaks in sensitivity to green light, right where the sun's emission spectrum reaches its maximum. This evolutionary harmony means we see most clearly in the wavelengths our star provides most abundantly. Our cone cells dominate in bright light, enabling color perception and fine detail, while rod cells take over in dimness, shifting our vision toward blue and dulling our sense of hue. This balance ensures that we see the natural world as the sun designs it, vivid, balanced, and detailed. Artists and photographers harness this biological calibration by using green tones to convey brightness without glare. When you gaze upon a sunlit field, you witness a perfect marriage between biology and astronomy, an eye evolved to read its native star. Yet light behaves differently under other conditions. Red light, for instance, travels farthest through fog and dust. Its longer wavelength scatters less than shorter blue or violet rays, allowing it to remain visible when others fade. This is why brake lights, warning signals, and sunsets share the same crimson hue. Red endures when the world grows hazy. It also explains why distant stars appear redder through interstellar dust, and why some deep-sea creatures are tinted red. They vanish into darkness since red light cannot reach those depths. Thus, light governs both what is seen and what remains hidden. On cloudy days, sunlight softens into a gentle, diffused glow. Clouds act as immense natural diffusers, scattering light in every direction and erasing sharp shadows. Under such illumination, colors appear truer, textures richer, and contrasts milder. Artists prize this quality for portraits and landscapes because it flatters the subject and evokes tranquility. In architecture, translucent materials mimic this effect, creating spaces bathed in calm equilibrium. Though many associate overcast skies with gloom, the light itself is remarkably kind, balanced, soothing, and revealing the world's details in quiet perfection. Light's behavior changes again during rare celestial alignments. In a total solar eclipse, the moon conceals the sun's blinding face, allowing the corona, the sun's ethereal outer atmosphere, to shine. This delicate halo, invisible under normal conditions, extends for millions of kilometers, its tendrils shaped by magnetic fields. For a few fleeting minutes, the world plunges into twilight as the sun's hidden radiance becomes visible, a ghostly crown shimmering in silence. Scientists study the corona to understand the solar wind and magnetic flows that shape space weather. To observers, it is an awe-filled reminder that even overwhelming brilliance conceals subtler beauty awaiting its moment to emerge. Beyond our solar system, the faint combined glow of all galaxies fills the universe with a diffuse radiance known as the cosmic optical background. Though imperceptible to the naked eye, instruments have detected this ancient light, the cumulative echo of billions of stars across cosmic history. Each photon within it is a relic, a traveler from the dawn of time, carrying the story of creation in its wavelength. This glow is not merely background illumination, it is a cosmic memory, the quiet hum of existence itself, a faint whisper of every sun that has ever shone. Together, these stories of light, from sacred fires to cosmic halos, from entangled photons to eclipses, reveal its dual role as both the builder and messenger of reality. Light is not only what allows us to see but what connects us to the universe's oldest truths. It is energy, structure, motion, and information all at once. Whether filtered through ancient crystal or quantum fiber, whether diffused through clouds or reflected from the distant edge of a galaxy, it tells a single, endless story, that every moment of perception, every spark of knowledge, and every act of wonder is a form of illumination. ChatGPT can make M. The universe is a vast sea of radiance, the lingering shimmer of all the fires ever kindled by gravity, where even the darkest stretches between constellations are not voids but soft oceans of ancient light, an intergalactic whisper from everything that has ever shone. Within the hearts of stars, where nuclear fusion forges helium from hydrogen, two messengers are born, light, and neutrinos. Photons, the carriers of visible light, take thousands of years to escape the dense stellar interiors, bouncing endlessly between atoms before they emerge into space as the brilliant beams that warm our world. Neutrinos, however, are the ghost travelers of the cosmos. Almost without mass and barely interacting with matter, they pass unhindered through entire planets, including Earth, in countless numbers every second. These elusive particles escape a star's core almost instantly, carrying within them the story of the nuclear furnaces that power the universe. Deep beneath mountains and frozen under ice sheets, detectors built with immense sensitivity await the rare event when one of these ghostly travelers brushes against an atom, releasing a faint flash that reveals the hidden workings of stars and supernovae. Light and neutrinos thus form two sides of cosmic communication, one that illuminates from without and one that whispers from within, each tracing the invisible bonds that connect creation to consciousness. Every sunbeam that touches your skin arrives not alone but accompanied by a silent river of neutrinos, flowing eternally through you, through oceans and stone, through the very heart of the Earth itself. Before light could travel freely through space, the cosmos was not dark but opaque, a dense, blazing fog of plasma where photons were trapped, endlessly scattering off charged particles in an inferno too thick for transparency. As the young universe expanded and cooled, atoms began to form, and suddenly, light was free. This first dawn, when the cosmos became transparent, gave birth to what we now call the cosmic microwave background, a faint, ancient glow that still fills every corner of the sky. It is the oldest picture of the universe we can ever see, a frozen memory of when light first escaped matter's grasp. Over billions of years, this radiant echo has stretched and cooled with the expansion of space itself, transforming from searing brilliance into a near-frozen whisper, detectable today as microwaves that hum softly in every direction. The cosmic microwave background is proof that even the apparent emptiness of space is not nothing but the quiet afterglow of everything that has ever been. Every photon within that background has been traveling for nearly 14 billion years, untouched and unbroken, carrying within it the faintest imprint of the first structures that would grow into galaxies, stars, and eventually, life itself. What appears to our eyes as darkness between stars is, in truth, filled with this ancient light, a silent memory of the universe's birth still echoing in the fabric of space. Even in the depths of intergalactic voids where no stars shine, the universe continues to glow with this ghostly warmth, reminding us that emptiness is an illusion. Space hums with the residue of creation. Each photon that reaches us is a messenger, a letter written in the language of time and energy, describing its origin, the temperature, movement, and chemistry of the place it began. As it travels through the stretching cosmos, the photon's wavelength lengthens, its color reddens, and its energy cools, but its story endures. When it finally meets an eye, a telescope, or even a grain of dust, its ancient message is read and completed. To observe the night sky is to read a library of light, each beam carrying within it the memory of where it was born, whether deep inside a distant star, flung outward by a supernova's dying breath, or scattered gently by clouds of interstellar dust. Light is the storyteller of the cosmos, endlessly traveling, endlessly remembering, weaving time into visibility. From the first dawn of the universe, it has been our companion, shaping the stars, tracing the spirals of galaxies, painting the glowing edges of worlds that rise and fall in cosmic cycles. Every golden ray that filters through the trees, every glimmer that ripples across the sea, is a continuation of that ancient radiance, crossing unimaginable distances to find its way here. The light that surrounds you now, resting on your skin, glinting in your eyes, may have begun its journey before there were eyes to see, before Earth had oceans, before language or thought existed to name it. Some of it comes from the sun, burning bright and near, some from stars so far away that their light began its voyage before humanity's first breath. Yet it keeps coming, gently, endlessly. The same radiance that shimmers through nebulae and galaxies now glows faintly through your window, threading your life into the great tapestry of the universe. Wherever it travels, light remembers. It records every interaction, every atom it brushes, every field it crosses, carrying the fingerprints of creation itself. It tells of beginnings that have no true ending, of energy that changes form but never fades, of transformation and persistence, the eternal rhythm of existence. Even when darkness surrounds you, light is never gone. It simply rests, hidden, waiting to be seen again. As your thoughts slow and your breath softens, imagine that ancient radiance flowing quietly through you, the warmth in your chest, the calm behind your eyes, the soft glow that lingers in every heartbeat. You are not separate from the light of the universe but an expression of it, a brief gathering of starlight taking form before dissolving again into the endless glow. The atoms that make you once shone in stars, the light you see now once traveled through clouds of cosmic dust that would one day become worlds. Every moment of stillness connects you to that infinite cycle. When you close your eyes and drift toward sleep, the universe continues to hum softly, a lullaby of photons and neutrinos, of energy and silence intertwined. The same light that kindled galaxies now cradles your thoughts, wrapping them in warmth older than time. So breathe deeply and let that cosmic glow settle within you. You are part of the story light tells, an echo of the first dawn, a flicker of the same fire that burns across the stars. Let it soothe you, infinite and kind, as the universe whispers softly through the quiet of night, holding you in its gentle, radiant embrace.